The topic of our today's lecture is digital switching. We refer to our textbook, namely Telecommunication Switching, Traffic and Networks by J.E. Flood, and chapter number 5, which is Switching Networks. We will start with a brief introduction to switching. What do we mean by switching? Switching is basically the function that is done in a telephone exchange. What does a telephone exchange do? We request a telephone exchange to get us connected to a certain number, and this exchange manages to connect us to our desired destination so that we can initiate a voice call. All this system includes two areas. Number one is the signaling, and the second one is the transmission. That is the transmission of voice. What happens is that from a telephone set to a telephone exchange, we have got a baseband, which means that we've got an analog circuit. We are talking about right now we are talking about a local number, or local number over copper network. What happens is that we when we speak, our acoustic signal, a voice acoustic signal, converts to a voice channel, voice signal basically. And in the analog format, it is sent to the exchange in that particular format, but it rides over a 48 volts of DC, which is produced by a DC power plant present in the exchange. And if we go a little bit beyond that, let me tell you that that is maintained by a large battery storage banks. Now, coming back to our main topic, that is digital switching. Digital switching is managed by exchanges, and what it does, that a large number of telephones are connected to this exchange or the switch, and the switch connects us to our intended destination. And how do we tell the exchange that what is our intended destination? By dialing a certain number. When we dial a certain number, the telephone exchange has a stored program control part that knows where to connect our line in our circuit to the output site or the outlet site. There are two parts of an exchange, primarily the inlet part and the outlet part. There may be m number of inlets and n number of outlets. Then it is the responsibility of the machine within the exchange to connect a particular inlet to a particular outlet. And how is it controlled? It is controlled by the telephone number that we dial. And that telephone number that we dial, it is already present in the stored program control computer. And that computer manages to connect our request to that particular destination. When we go beyond our exchange, it decides which trunk group we have to forward our request or our link. And through that trunk group, it by engaging one particular trunk, it takes us to the desired exchange, and that second exchange that decides how to get to our desired number. It connects us to that number. So these are some basics of this digital switching. Now let's go to our second slide, which is about single stage networks. This slide shows basically a space switch. You can see a space switch which is shown as a matrix of cross points. It is basically figure 3.11 or 3.11 of this particular book that we are following by J. Flood. It shows we have got M number of inlets and N number of outlets. You can see the wires going upwards also, but there's nothing shown upwards. Basically, we've got the stored program control placed upwards. By M inlets, we mean that these are M competing users who want to get connected to a certain outlet on the which is one of those N outlets, one of the N outlets it wants to connect to. The figure 5.1 shows the symbols that we use for switches, for a single stage switch. These are two types of symbols that we use normally. By the way, in the matrix of cross points, what we use earlier or historically, we have been using relays or contacts for crossbars crossbars. But digitally, what we can do is that we can use AND gates, and two inputs of one particular AND gate would consist of one input from among one of the inlets from M inlets and one input from the stored program control computer. The price of a telephone exchange depends upon two things or two factors. The first factor is a constant factor, which includes the items that have a constant rate or constant price. For example, the air conditioning, the infrastructure, and things like that. Also, the stored program control is one of those things. While the number of cross points is the variable part, which differs from an exchange to exchange. As the number of cross points increases, the price of the exchange increases. So this is a very important point that we need to keep in view. In our previous slide, we have shown a matrix of cross points, which is basically a single stage network. It shows a full availability that no calls are lost unless all outgoing trunks are busy. It means that all incoming trunks or all incoming lines have the capacity to connect to any of the outlets. There is no restriction. Since there is no restriction, it is a full availability network. The maximum possible simultaneous connections is the lesser of M and N. M is the number of inlets and N is the number of outlets. If M is the smaller number, then the total number of calls that can be handled by this exchange at one particular time would be M. Otherwise, it would be N. But if M is equal to N, then the number of cross points would be N square. And we call it C1. C means the number of cross points, and 1 means a single stage network. So cost increases as the square of the size of switch. As the number of number of inlets or outlets increases, the cost increases by the square of it. If we want to find the efficiency of such a system, it would be primarily in the numerator. We would keep the number of calls that can be handled at one particular time. We know that if this is an n by n network, there would be at the most n calls running at a time. And in the denominator, we have put the value of the number of cross points. So efficiency would be n over n square. N cancels with n and we get 1 over n, which is the proportion of cross points used at a particular time. Now let's calculate the efficiency of our system. If there are 100 inlets and 100 outlets, then the number of cross points would be 10,000. That is 100 into 100. Only 100 cross points are used at a time, which means that at the most 100 calls can run at a particular time, and this would give us 1% efficiency, because in the numerator we'll have 100 and in the denominator we will have 10,000. So several stages are used for exchanges of large customer base. This is the basic point or the basic disadvantage of a single stage network. That is, its efficiency is very low, as low as 1%. As we increase the number of inlets and outlets, it further reduces. One thing that we can do is make such a system in which we have half the number of cross points as compared of this. How can we do this? Let's see. Now let's put a diagonal on this matrix and remove the upper half part of this matrix. What we get is a system that works as good as a full matrix, but we have got rid of at least almost half of the cross points, and the new number of cross points would be 1 over 2 times n into n minus 1. Now let's see what is availability. Availability is the number of outgoing trunks to which an incoming trunk can obtain connection. For a root switch or a concentrator is a switch or an exchange in which there is a large number of inlets and a small number of outlets. It is not necessary for each incoming line to have the capacity to access to each outgoing trunk. It is adequate, it is okay if each incoming trunk has access to a sufficient number of trunks on each route. On each route means, for example, if we are placed in a certain town in the city, we want to get connected to some other town in that particular city. So there is a fair chance that both of these towns would have separate exchanges. So since there are many towns, we need to have many trunk groups going to each of those town switches. So it is adequate if each incoming trunk has access to sufficient number of trunks on each route to give a required grade of service. This is known as limited availability. Now let's see what is grading. Let's see. Let's suppose we have a basic example of 20 trunks, which are divided in two groups. Basically, two switch groups are handling these 20 trunks. Odd numbered trunks are handled by group 1 or the switch 1, and even number is handled by group 2. As you can see in this diagram, that group 2 has only access to the even numbered trunks, which are basically 10 in number. It does not have any access of those 10 trunks which have odd numbers. Similarly, group 2 does not have access to the even numbered. Group 1 does not have access to even numbered trunks. So in this way, both of these switches are separate. They have their own trunk groups. This is basically an example of limited availability, in which we can calculate the availability by the total number of trunks and divide it by the number of groups or the number of switches. Total number of trunks here is 20, and if we divide it by 2, which is the number of groups, we get 10. So such a system would have an availability of 10, which is lesser than being a full availability system. Now let's see, if we have got only 16 number of outgoing trunks and we want to maintain our grade of service to 0.01. How can we do it? We use a technique which is called grading. In this technique, we connect the least significant 4 trunks on each of the group together. In this way, we have got 4 numbers, 4 trunks which are common, and 6 trunks each is separate. We can also define it in the form of this 5.4b diagram, in which we can see that the 6 of the columns are separate, which means that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. These are 6 columns. 6, it means that these are 6 trunks each. They are separate, while 13th, 14th, 15th and 16th are connected. This is called grading. In this way, we increase the availability of the system. For a 2 groups system, the progressive grading calculation or the design is quite easy, and we can get a unique solution. If the availability is K, the number of outgoing trunks N, and the number of graded groups G, which is 2, then if all the choices are individual trunks, then N is equal to G into K. If all choices are full commons, or it means that all are connected together, then N is equal to K. But if there is a mixture of it, then we can have an average of both of these, which would be half times G into K. This would be the case when N ranges from K to G into K. G is equal to 2N over K. Now, to have symmetrical grading, G must be an even number. Here availability K would be equal to S plus C. S means separate, and C means combined. So the number of separate columns and number of combined columns. The number of trunks is equal to n, which is 2 into s plus c, where s is equal to n minus k and c is equal to 2k minus n. You can also make use of my calculation done in another YouTube video that I have already uploaded on this subject, in which I have been teaching from the book, and I have also solved an example which is already solved on page number 123, but I have explained it much further because many of the students complained that it was difficult for them to understand it. So I have elaborated it further. Now let's see what would happen if we have more than 2 number of groups. For example, in this slide you can see 4 groups, and we have got 3 examples of it. In part A, we have got one column which is completely separate, 2 columns which are completely connected, and 1, 2, 3, 4, 5, 6, 7 columns in which we have partial connections. Partial connections are the ones in which 2 trunks each in each column is connected. In B part, we have got 2 separates, 4 are partially connected and 4 are fully connected. In part C, we have got 3 separates, 1 partially connected, and 1, 2, 3, 4, 5, 6 are completely connected. In this way, we are handling 20 trunks. If we add them up, we can see that, for example, in part number 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. In each of the case, in C part, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we are handling 20 trunks in each. Now the next target would be to find out which case is the best. In slide number 10, to find out which design is the best, basically we see that the difference, we see that the sum of the successive differences should be the minimum, and that is given in basically equation 5.6. You can read it, and I have explained it in detail in my other video that I have already uploaded on YouTube. You can check this out also. So in this way, we find out that the B part, or the design shown in the B diagram, that is the best, because we get the least number of sum of successive differences. This is basically done in example number 5.1. Now let's see if we are able to get some more trunks at our disposal. What would we do? What we would do is that we would increase the number of trunks on the separate side. So earlier, if we had 20 trunks, we selected the B diagram on the 10th slide. What we would do is that we would increase 2 more separate columns, or the 2 more columns in which the trunks are separate from each other. While increasing the number and while increasing only one with partial connectivity or partial common trunks, and we will keep while we have also reduced the number of fully common columns from 4 to 3. There are other ways of designing a grading also. For example, you can see in figure 5.6 skipped grading, in which columns 4 and 5 are a little bit unfamiliar, but this is quite easy to implement. So if we have a situation, we can improve upon it by using skipped grading or even homogeneous grading, that is shown in the next slide. Now let's see what is the effect of availability on the relationship between traffic in Erlangs to the number of trunks required, while keeping the grade of service as a constant. For example, we keep grade of service B equal to 0.002. You can see in this diagram, in this curve, that as we move away from full availability scenario, that is, in the full availability scenario, we have got a straight line which defines the relationship between the traffic in Erlangs A and the number of trunks required N. Basically, let me tell you, this is the same line that is basically defined in the Erlang B formula. The Erlang B table that you have already studied in chapter number 4 regarding the traffic analysis, basically that table is defined based upon full availability. It considers full availability, but as we have different types of switching systems, the availability is reduced, and we have to do some compromise on it. But as we compromise on the availability and the availability becomes limited more and more, for example, in this example, in this diagram, it is shown that it goes to k is equal to 40, then k is equal to 20, then 10, then 5. As it is reduced, the line becomes steeper and steeper.